This is not a black hole. This is something that might be even stranger. A magnetar. An object so extreme that it breaks the rules of physics we thought were unbreakable. If you enjoy uncovering the universe's darkest secrets, hit that like button and subscribe, because what we're about to explore will change how you see the night sky. Prepare yourselves. We begin. A massive star reaches the end of its life. It has burned for millions of years, fusing elements in its core, building heavier and heavier atoms. Then the fuel runs out. In less than a second, the core collapses. The outer layers rebound in a supernova explosion that outshines entire galaxies. Everyone knows this story. But here's what they don't tell you. Not every stellar corpse becomes a black hole. When the star is just heavy enough, between 8 and 20 times the mass of our star, something different happens. The core doesn't collapse completely into a singularity. Instead, it stops. It crushes down to a sphere just 12 to 15 miles across, but it doesn't vanish into a black hole. What remains is a neutron star, a city-sized ball of matter so dense that a teaspoon of it would weigh as much as Mount Everest. But some neutron stars are born with a twist, literally. When the core collapses, it spins faster and faster, like an ice skater pulling in their arms. The magnetic field that existed in the original star gets compressed too. Squeezed into that tiny space, the magnetic field intensifies to levels that should not be possible. The result is a magnetar. This is confirmed science, not theory. We've detected these objects, we've measured their emissions, and the numbers are terrifying. A magnetar's magnetic field reaches strengths of 10 to the 15th Gauss. That's 1 quadrillion times stronger than Earth's magnetic field. It's 1,000 times more powerful than a typical neutron star. At that strength, the magnetic field itself becomes dangerous. Picture this. If a magnetar existed halfway between Earth and the Moon, roughly 120,000 miles away, it would erase every piece of magnetic data on the planet. Credit cards, hard drives, everything. But that's the least of our problems. The real danger is what that field does to matter itself. Because here's where physics starts breaking. At distances closer than 600 miles from a magnetar, the magnetic field becomes so intense that it warps the shape of atoms. Electrons, which normally orbit in spheres, get stretched into thin needles. Atoms stop behaving like atoms. The very building blocks of chemistry cease to function normally. And this is just the beginning. What happens when you get even closer? Imagine crushing our star down to the size of a city. Not Hollywood's version of crushing, real physics crushing. Every atom smashed so tight that there's no space left between them. That's what you're dealing with. A magnetar is roughly 12 miles in diameter. You could drive across it in 15 minutes, yet packed into that impossibly small sphere is 1.4 times the mass of our entire star. This isn't an estimate. Scientists have measured magnetar masses through their gravitational effects on nearby objects and the frequency of their pulses. The numbers are consistent and deeply disturbing. How does this work? In normal matter, atoms are mostly empty space. The nucleus sits in the center, electrons orbit far away, and between them is nothing. But when a star collapses into a neutron star, gravity crushes everything together. The electrons get forced into the nucleus, combining with protons to form neutrons. What remains is neutrons packed shoulder to shoulder, with no gaps. This creates matter at nuclear density. That means 1 cubic inch of magnetar material would weigh over 600 million tons. A sugar cube of this stuff would weigh more than all of humanity combined. If you somehow dropped a teaspoon of it onto Earth, it would slice through the ground like it wasn't there, punching straight through to the other side of the planet. The density is so extreme that the surface gravity becomes nightmarish. Stand on a magnetar, and you'd experience gravity 200 billion times stronger than Earth's. That's 2 times 10 to the 11th. You wouldn't just be crushed. Your atoms would be ripped apart and smeared across the surface in a layer 1 atom thick. But even this isn't the strangest part. Because magnetars don't just sit still. Their surfaces move, they crack, they quake. And when that happens, the entire universe notices. The magnetic field holds the magnetar's crust in place, like a vice. But the crust itself is crystalline iron, harder than diamond, floating on a sea of superfluid neutrons. As the magnetar spins and its magnetic field shifts, stress builds up in this crust. Eventually, something has to give. What comes next makes earthquakes look gentle. On December 27, 2004, something hit Earth. Not physically, but every satellite in orbit detected it. Radio telescopes around the world went haywire. The ionosphere, 60 miles above us, was suddenly illuminated. Scientists scrambled to figure out what happened. The source was 50,000 light-years away, a magnetar designated SGR 1800-6-20, and it had cracked. This wasn't a small event. When a magnetar's crust fractures, it releases energy that makes our most powerful weapons look like firecrackers. The December 27 event released more energy in 1/10 of a second than our star produces in 150,000 years. From 50,000 light-years away, it was brighter than a full moon to our satellites. This is confirmed data from NASA and multiple observatories. Think about that distance, light traveling for 50,000 years, and the burst still arrived strong enough to affect our planet's atmosphere. If this magnetar had been just 10 light-years away, the same distance as some of our nearest stars, the radiation would have stripped away Earth's ozone layer. Complex life would have ended. But what actually happens during a starquake? The magnetar's iron crust, under immense magnetic stress, suddenly shifts. It might move less than a millimeter. That's it, a fraction of an inch. But when you're moving crystalline iron harder than diamond, packed at nuclear density, even a millimeter displacement releases unimaginable energy. The magnetic field lines snap and reconnect violently, like rubber bands stretched to their limit and released all at once. This magnetic reconnection accelerates particles to nearly the speed of light. Gamma rays and X-rays spray out in all directions. The magnetar rings like a bell, its vibrations creating pulses we can detect across the galaxy. These starquakes can continue for weeks. The magnetar sends out aftershocks, each one releasing more energy than our star produces in years. The surface settles into a new configuration, slightly different from before. The magnetic field geometry shifts, and then it might stay quiet for years or decades. Or it might crack again tomorrow. We can't predict it. Each magnetar behaves differently. Some are active, erupting multiple times per year. Others go silent for decades before suddenly awakening. We're still trying to understand the pattern. Because the real mystery is what powers all of this. Where does a magnetar get the energy to keep doing this? You can't see a magnetar's field, but it's there, always. A sphere of twisted magnetic energy surrounding the dead star, reaching out hundreds of miles in every direction. And this field doesn't just attract metal, it destroys reality. At 600 miles from a magnetar, the magnetic field strength hits about 1 billion Gauss. That's confirmed through spectroscopic measurements of magnetar atmospheres and the cyclotron resonance features in their X-ray spectra. At this distance, quantum mechanics starts failing. Here's what that means. Normally, light travels in straight lines through empty space, but near a magnetar, light bends. Not because of gravity this way, but because of magnetism. The magnetic field is so strong that it affects the vacuum itself, something called vacuum birefringence. Photons traveling through this space split into two beams based on their polarization. Space itself becomes birefringent, like looking through a crystal. But it gets worse for anything with matter. Remember, atoms are held together by electromagnetic forces. Electrons orbit nuclei because of electric attraction, but a magnetar's magnetic field is strong enough to overwhelm these forces. The field doesn't just tug on electrons, it deforms them. At distances inside 600 miles, atoms elongate into needle shapes. The electron clouds that should be spherical get stretched along the magnetic field lines. Chemical bonds stop working the way they should. Molecules can't form properly. Complex chemistry becomes impossible. For any living thing, this is instant death. Not from heat, not from radiation, though there's plenty of that, but from the fundamental breakdown of molecular structure. Your cells would stop functioning before you even felt pain. The proteins that run your body would unfold. DNA would unravel. You'd come apart at the molecular level. Nothing we've built could survive this either. Spacecraft hulls would have their atomic bonds disrupted. Electronics would fail instantly, as the magnetic field induces currents millions of times stronger than they're designed to handle. Even light itself struggles to escape, bending and splitting as it fights through the distorted space. And this is all assuming you could somehow survive the radiation, which you couldn't, because magnetars don't just sit quietly in their magnetic cocoons. They scream. The field isn't static. It shifts, twists, and reconnects constantly, even between major starquakes. Each reconnection event sends out bursts of X-rays and gamma rays. These aren't gentle pulses. They're focused beams of high-energy radiation powerful enough to ionize anything in their path. But compared to what the field does to space itself, even this seems almost normal. Light is supposed to be simple, photons traveling in straight lines, unaffected by magnetic fields. That's what we learned. That's what works everywhere else in the universe. But near a magnetar, this rule breaks down completely. Scientists first predicted this in the 1930s, but they thought it would never matter. The effect, called photon splitting and vacuum birefringence, only becomes significant in magnetic fields approaching 10 to the 13th Gauss or higher. No natural object should reach that strength. Then we found magnetars. Here's what happens. In normal space, a vacuum is truly empty, but quantum mechanics tells us that's not quite true. Even in a perfect vacuum, virtual particles constantly pop in and out of existence. Electron-positron pairs appear for impossibly brief moments, then annihilate each other. We can't see this happening, but it's real. It's been measured in laboratories through the Casimir effect. Near a magnetar, the magnetic field is so strong that it polarizes this quantum vacuum. The virtual particles align with the field before they disappear. This alignment changes how light travels through space. The vacuum effectively becomes a medium, like air or glass, but made of quantum fluctuations. Light passing through splits into two beams with different polarizations. One beam polarized parallel to the magnetic field, another perpendicular to it. They travel at slightly different speeds. This is vacuum birefringence, and we've confirmed it through observations of magnetar spectra. The light arriving from these objects shows exactly the polarization patterns this theory predicts. But there's another effect, even stranger. At even higher field strengths, above 10 to the 13th Gauss, individual photons can split. A single high-energy gamma-ray photon can spontaneously divide into 2 or 3 lower-energy photons. This isn't science fiction. This is quantum electrodynamics pushed to its absolute limit. We've observed this indirectly. When magnetars have major flares, the spectrum of radiation we detect doesn't match what we'd expect from a simple hot surface. There are features, dips, and peaks in the spectrum that only make sense if photon splitting is occurring. The high-energy gamma rays are splitting into lower-energy X-rays before they reach us. This means that magnetars are natural laboratories for testing quantum mechanics in conditions we can never recreate on Earth. Our most powerful magnets reach maybe 45 Tesla, about 450,000 Gauss. A magnetar's field is roughly 2 billion times stronger. It's testing physics in a regime we can only dream of accessing artificially. And yet, this isn't even the most extreme thing magnetars do, because sometimes they don't just bend light, they weaponize it. March 5th, 1979. Every satellite orbiting Earth picked up something impossible. A wave of gamma rays and X-rays slammed into our planet's atmosphere with such intensity that it ionized the upper layers. Scientists initially thought it was a nuclear attack. The burst lasted for only 1/5 of a second, but in that instant, it delivered more energy than our star produces in 1,000 years. The source was a magnetar in the constellation Norma, about 30,000 light-years away. Designated SGR 0505-66. What we witnessed was a massive magnetic flare, the largest ever recorded. This is fully documented. The data came from Soviet Venera spacecraft, American satellites, and observatories worldwide. The event was so powerful that it remains the brightest burst of energy ever detected from beyond our solar system. But here's what makes it truly terrifying. That energy traveled for 30,000 years through empty space. It spread out over an expanding sphere. By the time it reached Earth, it had diluted across an area trillions of miles wide, and it still hit us hard enough to disrupt satellites and alter our ionosphere. Calculate backwards, and the numbers become nightmarish. At the moment of the burst, the magnetar released roughly 10 to the 46 joules of energy. That's more energy than an entire galaxy of 200 billion stars produces in several years, from a single object 12 miles across, in 1/5 of a second. How is this even possible? The leading theory involves catastrophic magnetic field reorganization. The magnetar's magnetic field, already at impossible strengths, became unstable. Magnetic field lines twisted and tangled over years or decades until they couldn't sustain the configuration anymore. Then they snapped. Imagine rubber bands wrapped around a ball, twisted tighter and tighter. Eventually, they break and whip back violently. But these aren't rubber bands. These are magnetic field lines carrying energy equivalent to the mass of small moons, according to Einstein's equation linking mass and energy. When they reconnect, all that energy has to go somewhere. It goes into accelerating particles. Electrons and ions get flung outward at 99% of light speed. These particles slam into the magnetar's own magnetic field further out, creating cascades of gamma rays through a process called synchrotron radiation. The magnetar effectively creates a massive gamma ray cannon, firing in all directions. For months after the March 1979 event, astronomers detected a pulsing X-ray source at the same location. The magnetar was still vibrating from the violence of the flare, sending out regular pulses every 8 seconds as it rotated. Even after the catastrophic release, it still had enough energy to outshine thousands of normal stars. And this raises a disturbing question. If magnetars can do this once, can they do it again? Can they do it bigger? Nobody was looking for magnetars. The word didn't even exist yet. Scientists in the 1970s were still wrapping their heads around neutron stars and pulsars, those rapidly spinning stellar remnants that sent out regular radio pulses. Then, on March 5, 1979, the universe decided to introduce us to something far more violent. The gamma ray burst that hit Earth that day didn't fit any existing model. It was too bright, too brief, and too energetic. It came from a fixed point in the sky, not from a distant galaxy. And in the months after, that same spot kept pulsing with X-rays every 8 seconds. This wasn't a pulsar behaving normally. This was something else entirely. Scientists called it a soft gamma repeater, or SGR. The name described what they saw but not what it was. It repeated, unlike most gamma ray bursts. And the spectrum was softer, meaning lower energy than typical gamma ray bursts from cosmological distances. But what could cause such behavior? Robert Duncan and Christopher Thompson proposed the answer in 1992. They calculated that a neutron star with a magnetic field powerful enough could store enormous energy in its twisted magnetic field lines. When those field lines snapped and reconnected, they would release bursts of gamma rays and X-rays. They called these objects magnetars, combining magnetic and star. The theory was controversial at first. Some scientists argued that magnetic fields couldn't reach such extreme strengths. Others questioned whether the field could remain stable. But observations kept piling up. More SGRs were found. Their behaviors matched magnetar predictions. And in 1998, researchers finally measured a magnetic field strength directly. They did this by observing cyclotron resonance features in the X-ray spectrum of a magnetar. When charged particles spiral in a magnetic field, they emit radiation at specific frequencies determined by the field strength. By measuring these frequencies in the X-ray light coming from magnetars, scientists calculated fields of 10 to the 14th to 10 to the 15th Gauss, exactly what Duncan and Thompson had predicted. Since then, we've identified about 30 confirmed magnetars in our galaxy and nearby galaxies. There are probably more we haven't found yet, either because they're dormant or hidden behind dust. Each one we study reveals new mysteries. Some are hyperactive, bursting multiple times per year. Others stay silent for decades. Some emit radio waves. Others don't. We're still learning the rules. But the discovery taught us something profound. The universe can create objects more extreme than we imagined. And if magnetars exist, pushing magnetic fields to their theoretical limits, what else might be out there, pushing other forces to their breaking points? August 27, 1998. The Rossi X-ray Timing Explorer satellite was doing routine observations of the sky when something extraordinary happened. A magnetar designated SGR 1900 plus 14, erupted in a massive flare. The burst was so intense that it saturated the satellite's detectors, overwhelming them with more X-rays than they were designed to handle. For several hours, the telescope was effectively blind. Its instruments had to reset and recalibrate. Engineers on the ground worried about permanent damage. This wasn't a design flaw. The satellite was built to study X-ray sources, but nobody anticipated an object that could suddenly become 100,000 times brighter in less than a second. This event wasn't unique. Multiple X-ray satellites over the years have been temporarily disabled by magnetar flares. In 2004, when SGR 1800-6-20 had its giant flare, it affected over a dozen spacecraft. Swift, Integral, RHESI, and others all recorded the burst. Some instruments went into protective modes. Others had their data corrupted by the sheer intensity of the radiation. Think about what this means. These satellites orbit Earth, about 93 million miles from our star. They're designed to observe X-ray sources billions of light years away. They have filters, shielding, and safety protocols to handle intense radiation, yet a magnetar tens of thousands of light years away can still overwhelm them. The implications are staggering. If a magnetar flare can blind a satellite across interstellar distances, what would it do up close? The answer is nothing survives. Any spacecraft within several light years of a major magnetar flare would be fried instantly. The radiation would induce currents in every circuit, melting electronics. Solar panels would degrade from the bombardment. Shielding would be useless against such intensity. But here's the really concerning part. We have no warning system. Magnetars don't announce when they're about to erupt. There's no precursor we can detect. One moment they're relatively quiet, sending out steady X-ray emission. The next moment, they explode with energy equivalent to thousands of supernovas compressed into fractions of a second. For future space exploration, this is a hidden danger. As we send probes deeper into our galaxy, they might encounter magnetars we haven't catalogued yet. A probe could be cruising through interstellar space, completely unaware that a dormant magnetar lies a few light years away. Then, without warning, that magnetar wakes up. The probe would die before its sensors even registered what happened. Scientists are now working on better detection methods. They want to map every magnetar in our galaxy and monitor them constantly. Early warning could save missions. But there's a problem. Dormant magnetars are almost invisible. They emit so little radiation that we can barely detect them. We might have dozens or hundreds lurking in our galaxy, completely unknown. And each one is a loaded weapon, waiting to fire. Our galaxy contains roughly 200 billion stars. About 1 billion of those will eventually explode as supernovas. Many will leave behind neutron stars. Scientists estimate there might be 100 million neutron stars scattered throughout the Milky Way. Yet we've only confirmed about 30 magnetars. What makes them so rare? The answer starts with how they're born. Not every neutron star becomes a magnetar. The original star needs specific conditions. It must be massive enough to produce a neutron star, but not so massive that it collapses into a black hole. That's a narrow range, roughly 8 to 20 times our star's mass. But mass alone isn't enough. The star also needs to be spinning rapidly when it collapses. As the core compresses, conservation of angular momentum makes it spin faster. This spinning, combined with the convective motions in the collapsing material, creates a dynamo effect. This dynamo amplifies the magnetic field to extreme levels. Think of it like a cosmic generator. The collapse itself generates the initial energy. The spinning motion organizes that energy into a coherent magnetic field. But this only works if conditions are just right. The rotation speed, the mass distribution, the initial magnetic field strength, all these factors have to align. It's rare. Even when a magnetar forms, it doesn't stay that way forever. The extreme magnetic field gradually decays over time. Scientists estimate that magnetars remain active for only about 10,000 years, maybe less. After that, the field weakens to normal neutron star levels. The object settles down, becoming an ordinary pulsar or simply a quiet neutron star. This short, active lifetime explains why we see so few. At any given moment, only a small fraction of neutron stars are in their magnetar phase. The rest have either not yet become magnetars or have already passed through that phase. It's a brief, violent stage in a neutron star's long existence. But there's another reason our count stays low: detection. Magnetars are small, about 12 miles across. They're incredibly distant, often tens of thousands of light years away. And unless they're actively flaring, they're dim. Many might be dormant right now, invisible to our telescopes, waiting for their next outburst. We only find magnetars when they do something dramatic. A major flare lights them up across the electromagnetic spectrum. Then we can study them, measure their properties, confirm they're magnetars. But a quiet magnetar could be lurking nearby, and we'd never know. In fact, scientists suspect there might be many more magnetars than we've confirmed, perhaps hundreds in our galaxy alone. Most are dormant, their surfaces cooling, their magnetic fields slowly decaying. They'll flare again eventually, years, decades, or centuries from now. But until then, they remain hidden, which means there might be one closer than we think. Distance usually means safety in space. A supernova 10,000 light-years away is spectacular but harmless. Even a gamma-ray burst, if it's not pointed directly at us, poses no threat from such distances. But magnetars change the calculation completely. Scientists have run the numbers, and they're disturbing. If a magnetar within 10 light-years of Earth experienced a giant flare, one comparable to the December 2004 event, the radiation would be devastating. The burst would hit our atmosphere with enough energy to destroy the ozone layer partially. UV radiation from our star would spike. Extinction events would follow. But here's what keeps astronomers up at night. 10 light-years is close. Very close. There are only about a dozen stars within that radius. The odds of a magnetar being that close are extremely low. But 10,000 light-years? There are millions of stars at that distance, and we know magnetars exist in that range. We've detected them. A hyperflare from 10,000 light-years away wouldn't destroy our ozone, but it would cause noticeable effects. The ionosphere would light up, satellites would be damaged, radio communications could fail, and if the flare was strong enough, if it reached the extreme end of what magnetars are theoretically capable of, even from that distance, it might cause biological harm. The worst-case scenario involves a magnetar hyperflare pointed directly at Earth. Remember, magnetars emit focused beams of radiation from their magnetic poles. As they rotate, these beams sweep across space like lighthouse beams. If Earth happened to be in the path during a giant flare, we'd receive the full intensity, not just scattered radiation. From 10,000 light-years, such a beam could deliver radiation doses comparable to being near a nuclear explosion. Not everywhere on Earth, just the side facing the magnetar at that moment. But that would be enough. Power grids would fail from the electromagnetic pulse, electronics would fry, and living tissue would absorb dangerous levels of gamma rays and X-rays. Scientists estimate that a magnetar hyperflare from this distance could increase cancer rates worldwide for decades afterward. It wouldn't be an immediate extinction event, but it would be a catastrophe. And there's no way to prepare, no warning system, no defense. The geological record might already contain evidence of past magnetar flares. Some mass extinctions have no clear cause. Researchers have looked for signs of increased radiation exposure in the fossil record. Certain layers show mutations and cellular damage consistent with radiation exposure, but the source remains unknown. Could a magnetar have fired at Earth millions of years ago? We can't prove it yet, but the possibility exists, and it's chilling. Because somewhere out there, right now, a magnetar might be building up stress in its crust. In years or decades, it will crack. Its magnetic field will unleash a beam of death into the galaxy, and all we can do is hope we're not in the way. Imagine standing on a magnetar's surface. You can't, because you'd be dead, but imagine it anyway. Under your feet, if you had feet, is a landscape that defies everything we know about solid matter. The crust is iron, pure iron, compressed to densities millions of times greater than steel. It's arranged in a crystalline structure so perfect that it makes diamonds look disordered. This is the hardest substance in the universe. Nothing we can create comes close. Laboratories have tried to simulate these conditions and failed. The pressures and densities are simply beyond our reach. But this iron isn't static. The intense magnetic field threads through it, creating currents and eddies of electric charge. These currents generate heat, not the kind of heat you feel from a fire. We're talking millions of degrees. The surface temperature of a young magnetar can reach 10 million degrees. That's hotter than the core of our star. At these temperatures, even crystalline iron starts to behave strangely. The outer layers, just the top few yards, exist in a state between solid and liquid. The atoms vibrate so violently that they can slip past each other, like a metal that's almost melting but held in place by the crushing gravity. Deeper down, the pressure increases and the material stays solid, but the surface has this weird plasticity. When a starquake happens, this iron crust cracks, but not like glass shattering. The crack moves at a significant fraction of light speed, propagating through the ultra-dense material faster than sound in normal matter. The two sides of the crack suddenly shift, creating a shear motion that releases the stored magnetic energy. The surface ripples. Waves move through the solid iron like water ripples in a pond, except these ripples are moving through material billions of times denser than water. The magnetar rings like a bell, oscillating at specific frequencies determined by its size, mass, and internal structure. These oscillations continue for weeks or months, gradually damping down as the energy dissipates. But the surface doesn't just crack and ring, it also erupts. The magnetic energy release heats material to billions of degrees in microseconds. Iron vaporizes despite the intense gravity trying to hold it down. A plume of ionized iron plasma, an atmosphere suddenly created by violence, rises above the surface. This atmosphere is temporary, lasting maybe seconds or minutes before gravity pulls it back down. During those brief moments, the magnetar has a real atmosphere, thin but detectable. Spectroscopic observations have actually captured this. When magnetars flare, their spectra show absorption lines from iron, silicon, and other elements. These lines tell us what the surface is made of and how hot it is. The data confirms our models. The surface is indeed iron, and it's indeed unimaginably hot. Beneath the crust lies something even stranger, a liquid layer of neutrons, unbound from protons, flowing freely. Scientists call this a neutron superfluid because it flows without any friction or viscosity. Deeper still, the neutrons might form exotic states of matter that we can barely describe with current physics. But all of that is hidden beneath the iron, and the iron itself is already beyond our comprehension. Most magnetars don't have atmospheres, not like Earth's atmosphere, anyway. The gravity is so intense that any gas would be pulled down and crushed into the surface almost instantly. But magnetars do have something, a layer so thin, it's barely there, yet so heavy it defies belief. Scientists call it a photosphere, though that's not quite accurate. It's the region where photons can finally escape from the dense material below. In normal stars, the photosphere is thousands of miles thick. In a magnetar, it's measured in centimeters, sometimes less, a layer just 1 atom thick. But that layer weighs millions of tons per square inch. The density is so high that a single cubic centimeter contains more mass than a mountain. The photons struggling to escape through this layer get scattered billions of times, bouncing between atoms and electrons before finally breaking free. This scattering alters the spectrum we observe, creating the unique fingerprints that identify magnetars. The magnetic field plays a crucial role here too. It's so strong that it confines any material trying to escape. Electrons, ions, everything gets trapped along magnetic field lines. They can move along these lines but not across them. The result is a highly structured atmosphere, more like columns and sheets than a uniform gas layer. When a magnetar flares, the magnetic field lines above the surface reconnect. This magnetic reconnection suddenly releases trapped material. Plasma that was held in magnetic loops gets flung outward at high speeds. For a brief time, the magnetar develops a real atmosphere, extending maybe 100 miles above the surface. This ejected material cools as it expands, emitting X-rays and gamma rays. We can observe this emission with our telescopes. The spectrum shows features that reveal the temperature, density, and magnetic field strength of the material. It's one of the few ways we can probe conditions near a magnetar's surface. But gravity always wins. The escaped material doesn't have enough velocity to reach escape velocity. It arcs back down, crashing into the surface at speeds of thousands of miles per second. The impact creates more X-rays, more heat, and sometimes triggers additional magnetic activity. The whole event can last hours or days. Between flares, the atmosphere essentially disappears. Individual atoms might hover temporarily before falling back. Particles trapped in magnetic field lines spiral endlessly, but there's no continuous gaseous layer, no weather, no atmospheric circulation, just crushing gravity, searing radiation, and magnetic field lines so twisted they form cages of force. This is as close to a naked stellar core as nature allows. The surface of a magnetar is matter at its limit, physics at its breaking point, and yet, somehow, it's stable, it exists. A 12-mile sphere of impossibility, floating in the dark, waiting to remind us that the universe still has secrets we can't explain. Einstein taught us that gravity warps space-time. The stronger the gravity, the more time slows down relative to an outside observer. We've tested this with atomic clocks on airplanes and satellites. The effect is real, but near a magnetar, time doesn't just slow down, it nearly stops. Calculate the gravitational time dilation at a magnetar's surface, and you get numbers that seem wrong. For every second that passes on the magnetar, roughly 1.3 seconds pass for someone far away. That's a 30% difference. If you somehow stood on a magnetar for 1 year, about 16 months would pass for the rest of the universe. This isn't speculation. The math is straightforward general relativity. We can measure it indirectly through the light coming from magnetars. Photons climbing out of the intense gravitational field lose energy. They get redshifted, their wavelengths stretched. The amount of redshift tells us exactly how strong the gravity is, and the calculations match theoretical predictions perfectly. But time dilation creates strange situations. Imagine watching a magnetar from a distance with a perfect telescope. You see its surface. A starquake happens. From your perspective, the crack spreads across the surface, more slowly than it would if you were right there. The oscillations that follow appear stretched out in time. The entire event looks like it's happening in slow motion. Meanwhile, if you were somehow on the surface, time would feel normal to you. The crack would spread at its true speed. The oscillations would ring at their natural frequency. You wouldn't notice anything strange about time itself. It's only when you compare your clock to a distant observer's clock that the difference appears. This has real consequences for the physics happening on the magnetar. Nuclear reactions, particle decays, all processes that depend on time, run at different rates depending on where you measure them. A neutron near the surface would decay more slowly from an outside perspective than a neutron far from the magnetar. The difference is measurable. Scientists use these time dilation effects to test general relativity in extreme conditions. Magnetars provide a natural laboratory where gravity is strong enough to create noticeable effects, but not so strong that it collapses into a black hole. They're right at the edge, the perfect testing ground. Some researchers have proposed that magnetars could be used for precision tests of alternative gravity theories. If general relativity breaks down anywhere, it would be here, where space-time is stretched to its limit. So far, the observations match Einstein's predictions. But we keep watching, keep measuring, hoping to find a crack in the theory. Because if general relativity does fail near magnetars, it would revolutionize physics. We'd need new theories to explain what holds these objects together, how they behave, why they don't collapse. The implications would ripple through every branch of science. But for now, Einstein still reigns. Time bends near magnetars, exactly as he predicted. And that bending is yet another way these objects warp reality itself. Here's a problem that keeps physicists awake. Magnetic fields decay. Always. Every magnet you've ever held will eventually lose its magnetism. The atoms that create the field slowly drift out of alignment. Energy dissipates as heat. It's inevitable. So why don't magnetar fields decay? They do decay, actually, but incredibly slowly. Scientists estimate a magnetar's field has a half-life of about 10,000 years. That means after 10,000 years, the field strength drops by half. After another 10,000, it halves again. Given enough time, a magnetar should become an ordinary neutron star with a much weaker field. But here's the mystery. The energy stored in a magnetar's magnetic field is enormous. We're talking about 10 to the 47 joules, roughly the mass energy equivalent of a small planet, according to Einstein's famous equation. That energy has to come from somewhere, and it has to be maintained somehow, at least for a while. The leading theory involves the magnetar's rotation. When a magnetar forms, it's spinning incredibly fast, maybe 1,000 times per second. This rotation, combined with convective motions in the newly formed neutron star, could generate the initial magnetic field through a dynamo process. It's similar to how Earth generates its magnetic field, but cranked up to impossible extremes. But there's a catch. For this to work, the magnetar needs a power source to drive the dynamo. Rotation provides some energy, but not enough. Scientists think the key might be in the magnetar's internal structure. Neutron stars aren't uniform spheres. They have layers, crusts, superfluid cores. Different layers might rotate at different speeds, creating shear forces. These forces could maintain the magnetic field. Another possibility involves exotic matter. In the core of a neutron star, pressures are so extreme that neutrons might break down into their constituent quarks. These quarks could form strange states of matter, like quark-gluon plasma or even stranger configurations. Some theories suggest that these exotic states have unique magnetic properties that could sustain ultra-strong fields. We don't know which theory is correct. Maybe all of them contribute. Maybe there's another mechanism we haven't thought of. The data we have isn't detailed enough to rule out options. We need more observations, better models, and perhaps new physics to fully understand how magnetars maintain their fields. But here's what we do know. The field is there. It's measured, it's confirmed, and it's doing things that shouldn't be possible according to our standard models of magnetic field decay. Magnetars are violating expectations, pushing beyond what we thought nature allowed. And every observation raises new questions. Some magnetars seem to have fields that are increasing rather than decreasing. How is that possible? Others show complex field geometries that don't match simple models. The field isn't just strong, it's structured, twisted, knotted in ways we're only beginning to map. These objects are telling us that we don't understand magnetic fields as well as we thought. Not at extreme energies, not in extreme conditions. And until we crack this mystery, magnetars will remain one step ahead of our theories. Not all magnetars behave the same way. Some are hyperactive, erupting dozens of times per year. Others go silent for decades, only to suddenly wake up with a massive flare. This inconsistency has puzzled scientists since we first discovered these objects. What determines a magnetar's behavior? SGR 1800 6-20 was dormant for over 20 years, quiet, unassuming. Then, on December 27, 2004, it produced the largest burst ever recorded. The entire astronomical community was stunned. What triggered it? Why then? We still don't have complete answers. Compare that to SGR 1900+14, one of the most active magnetars known. Between 1998 and 2002, it erupted hundreds of times. Some bursts were small, others were major events. Then it calmed down. Now it's relatively quiet, only producing occasional bursts. What changed? Scientists have proposed several theories. One involves the magnetar's age. Young magnetars, recently formed, might be more active because their crusts are still settling. The magnetic field is still reorganizing, causing frequent starquakes and flares. As the magnetar ages, it stabilizes and activity decreases. This matches some observations, but not all. Another theory focuses on the magnetic field geometry. If the field is highly twisted and complex, it might store more energy and lead to more frequent reconnection events. Simpler field geometries might be more stable, but we can't directly observe a magnetar's field structure. We have to infer it from the timing and spectrum of bursts, which leaves a lot of uncertainty. Temperature might also play a role. Magnetars cool over time as they radiate away their internal heat. A hotter magnetar might have a more fluid interior, allowing the crust and core to interact more dynamically. This could trigger more starquakes. As the magnetar cools, the interior stiffens and activity drops. This theory has some support from thermal emission observations, but none of these theories fully explain the data. Some magnetars don't follow the expected patterns. They stay active longer than they should, or they go quiet earlier than predicted. And the sudden awakening of dormant magnetars, like the 2004 event, suggests that even a seemingly dead magnetar can harbor hidden stresses ready to erupt. There might also be external factors we haven't considered. Could interactions with nearby objects trigger flares? If a magnetar is in a binary system, maybe the companion star's gravitational influence causes tidal stresses that eventually lead to starquakes. Most known magnetars appear to be isolated, but we might have missed companions in some cases. Or perhaps it's purely random. The stresses build up chaotically, and when the crust finally cracks, depends on countless tiny factors we can't measure or predict. Like earthquakes on Earth, magnetar flares might be fundamentally unpredictable beyond statistical probabilities. This unpredictability is both fascinating and frustrating. It means every magnetar is a unique case study. It also means we can't forecast when the next major flare will happen. All we can do is watch, wait, and hope our telescopes are pointed in the right direction when it occurs. Gamma-ray bursts are the brightest events in the universe. For a few seconds, a gamma-ray burst can outshine every other object in the observable cosmos combined. Astronomers have detected these bursts from galaxies billions of light-years away, so distant that the light has traveled for most of the universe's history, and magnetars might be creating some of them. Most gamma-ray bursts come from two sources we've identified. Long-duration bursts, lasting more than 2 seconds, come from massive stars collapsing into black holes. Short-duration bursts, under 2 seconds, come from neutron-star collisions. But there's a third category. Some bursts don't fit either model. They're too short to be collapsing stars, too bright to be ordinary neutron star mergers, and their spectra show features that match magnetar flares. In 2004, when SGR 1800-6-20 had its giant flare, it was briefly visible from the Andromeda Galaxy, 2.5 million light-years away. If that same event had occurred in a distant galaxy, say 10 billion light-years away, we would have detected it as a short gamma-ray burst. We might have classified it as a neutron star merger or some other event, never guessing it was actually a magnetar. This realization changed how we interpret gamma-ray bursts. Some bursts we've been attributing to other causes might actually be magnetar giant flares. If true, it means magnetars are even more common than we thought. Every galaxy might host dozens or hundreds of these objects, occasionally producing bursts we can detect across cosmic distances. But there's an even more intriguing connection. Some scientists think magnetars might power certain types of supernovas, not the supernova that creates the magnetar, but later events. Here's how it could work. A young magnetar, spinning incredibly fast, could inject energy into the expanding debris of its parent supernova. This energy would make the supernova appear much brighter and last much longer than normal. We've observed supernovas that don't match standard models. They're too bright or they fade too slowly. Researchers call these superluminous supernovas. Some have spectra consistent with magnetar-powered emission. The magnetar's spin-down energy, as it gradually slows due to magnetic braking, gets converted into radiation that lights up the surrounding gas. It's like having a cosmic light bulb inside the supernova remnant. If this is correct, magnetars aren't just interesting in their own right. They're key players in multiple cosmic phenomena. They shape supernova evolution. They create gamma-ray bursts. They might even seed the universe with heavy elements through their violent eruptions. The material they blast into space, enriched with iron and other metals, could contribute to the chemical makeup of future generations of stars and planets. This web of connections shows how important magnetars are to cosmic ecology. They're not isolated oddities. They're part of the grand cycle of stellar birth, life, and death. And every time we study one, we learn something new about how the universe works. Imagine this scenario: a massive star, roughly 200 light-years from our solar system, reaches the end of its life. It explodes in a supernova. We see the light show, beautiful, harmless at that distance. But the core collapses into a magnetar. What happens next? Initially, nothing. 200 light-years is far enough that even a magnetar poses no immediate threat. Its magnetic field, while intense, drops off rapidly with distance. At 200 light-years, the field strength would be negligible. We wouldn't detect anything unusual beyond the supernova itself. But magnetars don't stay quiet. Within years or decades, it would have its first major flare. Let's say it produces a burst comparable to the December 2004 event. The radiation would travel toward Earth at light speed. 200 years later, it would arrive. The burst would light up our night sky, not as bright as the full moon, but noticeable. A point of light suddenly appearing, brighter than any star. It would last less than a second, then fade. Astronomers would scramble to figure out what they just witnessed. Telescopes would focus on the location, and they would find the magnetar, still pulsing, still sending out X-rays. But here's the concerning part. The radiation dose Earth receives from 200 light-years would be minor. Background levels would spike slightly. Satellites might experience minor glitches, but nothing catastrophic. Now imagine the magnetar is only 20 light-years away. At 20 light-years, a giant flare would be dangerous. The X-ray and gamma-ray dose would penetrate our atmosphere significantly. The ozone layer would take damage. Not complete destruction, but enough to increase surface UV radiation for years. Cancer rates would climb. Ecosystems sensitive to UV would struggle. Marine plankton, which form the base of the ocean food chain, would die off in large numbers. At 10 light-years, we're in catastrophe territory. A magnetar giant flare from this distance would be an extinction-level event. The ozone layer would be shredded. UV radiation from our star would sterilize the surface. Complex life would retreat to caves and deep oceans. Some species would survive, but most wouldn't. Human civilization would face collapse. And here's the truly terrifying thought. We wouldn't know until it was over. The flare travels at light speed. There's no warning. One moment, everything is normal. The next, our sky lights up with deadly radiation. By the time we detect it, we're already bathed in it. There's no time to prepare, no chance to protect ourselves. Fortunately, the odds are extremely low. Massive stars capable of producing magnetars are rare. Most are far away. The nearest known massive star is probably over 100 light-years away. And even if it did go supernova, the chance of the core becoming a magnetar, rather than a black hole or regular neutron star, is maybe 1 in 10. And then the chance of it flaring toward Earth during its brief active lifetime is even smaller. But the universe is old and large. Somewhere, sometime, a civilization might not be so lucky. They might live near a magnetar, and when it wakes up, their story ends. Black holes get all the attention. They're the universe's ultimate destroyers, the objects that swallow everything. Nothing escapes, not even light. Pop culture loves them. Movies feature them as cosmic villains. But ask a physicist, which object is actually more dangerous? And you might get a surprising answer: magnetars. Here's the argument. Black holes destroy through gravity. Get too close, past the event horizon, and you're gone. But the event horizon is small. For a stellar mass black hole, maybe 60 miles across, stay outside that radius, and you're relatively safe. Yes, there's radiation from the accretion disk if the black hole is feeding, but a dormant black hole, one not actively consuming matter, is essentially invisible and harmless unless you fly directly into it. Magnetars kill at a distance. Their magnetic fields extend thousands of miles. Their radiation bursts travel across light years. They don't need to be close to cause damage. A magnetar could be sitting 10 light years away, and if it flares in your direction, you're dead. A black hole 10 light years away is just another dark object in space. The destructive range is completely different. Scientists have calculated the danger zones. For a black hole, the lethal radius is measured in thousands of miles at most. You have to be practically touching it for gravity to tear you apart. For a magnetar, the lethal radius extends to potentially dozens of light years. When accounting for giant flares, that's billions of times larger. But black hole advocates push back. They argue that black holes are forever. A magnetar is active for maybe 10,000 years. A black hole exists until the universe ends. Given enough time, a black hole will consume more matter, destroy more structure, and have a greater cumulative impact on the universe. They also point to supermassive black holes at galaxy centers. These monsters contain billions of times the mass of our star. When they're actively feeding, they create jets of radiation and matter that extend hundreds of thousands of light years. These jets sterilize entire regions of galaxies, preventing star formation and wiping out any life that might have emerged. No magnetar can compete with that scale of destruction. Yet the magnetar supporters have a counter-argument. Those supermassive black holes cause gradual destruction over millions of years. A magnetar flare is instant, civilization ending in less than a second. There's something uniquely terrifying about that immediacy. Black holes give you time, magnetars don't. There's also the question of which is more violent relative to size. A magnetar 12 miles across can release more energy in a fraction of a second than thousands of stars produce in years. A stellar mass black hole, even when feeding actively, can't match that energy output. Pound for pound, magnetars win. The debate remains unresolved. Both objects represent physics at its most extreme. Both can end worlds, but they do it differently. Black holes erase through gravity, slowly, inevitably. Magnetars attack with radiation and magnetism, suddenly, explosively. Maybe the real answer is that we should fear both. The universe has created multiple ways to destroy life, and arguing about which is worse seems pointless when either one near Earth would mean the end of everything we know. Every atom in your body except hydrogen came from stars. This isn't poetry, it's confirmed science. Carbon, oxygen, nitrogen, iron, all these elements were forged in stellar cores and scattered into space when stars died. But there's a mystery. Some heavy elements, the really massive ones, shouldn't exist in the quantities we observe. Creating elements heavier than iron requires specific conditions. You need intense neutron bombardment, temperatures in the billions of degrees, and precise timing. Supernovas provide some of this. Neutron-star collisions provide more. But calculations show these sources alone can't explain all the heavy elements we detect in the universe. Something else must be contributing. Enter magnetars. When a magnetar erupts, it doesn't just release radiation, it ejects matter. Neutron-rich material from the surface gets blasted into space at significant fractions of light speed. This material is incredibly dense, packed with neutrons that haven't yet decayed, and it's moving through a radiation field intense enough to drive nuclear reactions. These conditions are perfect for rapid neutron capture, the R process that creates heavy elements. Neutrons slam into existing nuclei, building heavier and heavier atoms in milliseconds. Gold, platinum, uranium, elements that are rare and precious on Earth, form in abundance during these violent events. The magnetar is essentially a cosmic foundry, manufacturing heavy elements through pure violence. Scientists have found evidence supporting this in meteorite samples. Some ancient meteorites contain isotope ratios that don't match supernova predictions. They show excess amounts of certain heavy elements, enriched beyond what standard models produce. The ratios match what you'd expect from R-process nucleosynthesis in extreme magnetic fields. The implications are staggering. Every gold atom in existence might have passed through a magnetar flare billions of years ago. The platinum in catalytic converters, the uranium in nuclear reactors, the rare earth elements in electronics, all possibly created during moments of unimaginable violence on magnetar surfaces. But there's more. The ejected material doesn't just float off into space. It slams into the surrounding gas and dust at high velocity, creating shockwaves. These shockwaves compress the material, triggering star formation. New stars, born from magnetar ejecta, would be enriched with heavy elements from the start. Their planets would have more metal, more complex chemistry, better conditions for life. This creates a feedback loop.